Hello, everyone. Welcome to Global Hack Week today. I'm super excited to see everyone in the chat. This is the first part of a three-parter series. This series, I'll be teaching y'all about recurrent neural networks and how you can use them to generate characters for your different games that you've been learning how to create this week, or even if you're just trying to kind of work on the game design of your application. This is a great way to make a bunch of characters for that game without needing to manually write them out. Before we dive into all that, I'd like to introduce myself. My name is Gabriella. I'm a coach here at Major League Hacking. I've been at Major League Hacking for about a year now. I'm really enthusiastic about both machine learning as well as Candy Crush. I don't play a ton of games in my free time, but I do play a good amount of Candy Crush, and I absolutely love playing that game. And I also want to call attention to the registration link for this particular event. If you haven't already, please register at the events.mlh.io link. I sent it in the chat, and it's also on screen. I'll give y'all a minute or two so you can register before we get actually started. All right, I think y'all had enough time to register for this particular event. Make sure you register your attendance for any of the workshops that you'll be attending throughout this week. But I'm going to kind of dive into the schedule for this particular workshop, and I'll give you a little bit of a heads up of what we'll be doing in the other two workshops as well. So a little bit of an agenda. First off, I'll give y'all an introduction to recurrent neural networks as well as gated recurrent units. And this will kind of show you a little bit of a basis of the concepts that we'll be diving into for overall for this workshop series. And I'll also talk you through kind of like what the overall gist of like what we're trying to accomplish with our model and how we're going to be calling that. Of course, throughout the entirety of this workshop, feel free to drop any questions you may have in the chat. I'm more than happy to answer those. I may not see them right away, but feel free to drop them in chat and I will answer those as we go throughout. And after I go through that introduction, I'll go into some game data preparation, where we're essentially preparing some data for our model, and we're also going through the installations and just kind of like preparing everything for the model. And then we'll finally end off the workshop by diving into more of that building and training the model, so we're able to generate different character names by the end of this workshop. And later on throughout the series, we'll be generating more information about our characters, such as their backstories and what their physical appearance looks like. So we're able to take those characteristics and put it into an API. So we're able to generate an image of what your characters look like, so you can kind of base your characters off of that in your games, which I think will be pretty fun and kind of like a unique application of recurrent neural networks. All right, so now on to the introduction, a little bit about recurrent neural networks and gated recurrent units if you're unfamiliar. So here is kind of like an overview of what neural networks are before we get into specifics of recurrent neural networks. So kind of like the overall view of what neural networks are. They are kind of like an interconnected group of nodes, and they're modeled after a simplification of you and I's brains' neurons. So as you may or may not know, our brains have neurons, and these are like firing different connections between one another for us to kind of like have thoughts and like memories, as well as be able to kind of like process information. Neural networks and artificial intelligence work somewhat similarly, but they're not quite as complex as like the human brain. As you can see here on the left, there's an image that's kind of representing what neural networks look like in machine learning. So we have the input layer, all of our hidden layers, as well as the output layer. You can see that there's a lot of different connections between the input and the hidden layers. This is a pretty like simplistic neural network diagram for neural networks that are a little bit deeper and utilized in deep learning. There will be multiple hidden layers. That kind of begins when there's two or more hidden layers. That's when deep learning kicks in, because these neural networks get much more complex. But as you can see, the input for each of the red circles is mapping to multiple of the different hidden layers. So input 1 is going to hidden layer neuron 1, 2, 3, and 4. And this is the case for input 2 and 3. So as you can see in neural networks, the more inputs you're given, the more complex the neural networks becomes. Kind of similarly to how our brains function, and the more neurons that are firing, the more complex our thought patterns can be, and like the more complex tasks we're able to handle. So now that I've kind of given you an overall description of what neural networks are, I'm going to dive a little bit more into an in-depth explanation of how they work in machine learning, and how we're able to utilize them in like real life and applications. So all of these nodes you see right here, the input nodes, the hidden nodes, and the output nodes are all connected by edges, which are modeled after synapses in the brain, if you're at all familiar with neural networks in the brain. If you come from a biology background, or perhaps a STEM background that focuses more on traditional sciences, you may be familiar with that makeup. But nodes, and also just kind of like let you know, nodes and neurons are kind of like an interchangeable word in this particular use case. So if you hear me using those two words, they mean essentially the same thing. Node is more particular to the application in machine learning, whereas neuron is, of course, more based in like the human brain. So all of these nodes or neurons are connected by edges. So all these arrows are kind of like a graphical representation of these edges. And a node receives signals from other connected nodes, and then we'll process them and send a signal based on their processing to another connected node. So in the case of a pretty simple neural network, it'll go from this node, it sends a signal to the hidden node. The hidden node will process the information. And in the case of our model, oftentimes it's doing some sort of converting or something with that information, which is like why it's being sent to the hidden layer in the first place. And after that process is done, maybe it's converting a particular type of number or text into another data type, or we're doing some sort of kind of connection on those different data types. After that process has been done, the node is done with it in the hidden layer, it's going to send a signal to the output layer, which is where kind of like the connection stops. But it's done kind of like in an interconnected way. So the input from this original input node is being sent out to a bunch of other nodes that are doing different processes, which is why they're being sent out in the first place. So they're pretty complex, but also this one node will be doing one particular type of processing on a bunch of different types of data. And kind of like it goes even more, I guess, like there's a bunch of different types of processing for 3+ types of data. And then we're left with like a really complex set of connections and inferences, which is why machine learning and the models it creates can be so powerful. Okay. Checking for questions. Doesn't look like we have any questions so far. So, okay, now that we were sending signals from one node to the other, they're being processed and sent to another connected node. The signal in machine learning is known as a real number, as opposed to something that's continuous. And after like the final signal is sent to the output node, what's happening in that particular instance in the output nodes is that it's outputting the activation function, which is calculated based on the signals and their weights. So because of like all of these conflicting, or maybe not conflicting, but maybe it's just all of these different signals. As you can see, there's a lot of different signals occurring in this like last section from the hidden layer to the output layer. It's not quite a very clear answer. So when we're calling that model, what happens is the node is outputting an activation function, which is calculated based on all the signals that we're receiving and how weighted they are. So for example, we have 4 nodes here. If they were all equally weighted, they'd all be weighted at 25%. So we take into consideration, for example, maybe this had a weight of 25% and it's outputting a 5. This has a weight of 10, a weight of 25, and it's outputting a 10. This one is outputting a weight of 5 and has a weight of 25, and this one is outputting 10 and has a weight of 25, we'd come with something like the output number would be closer to like 7.5 or something like that, because they're all weighted equally with those different numbers. But it gets a little bit more accurate because you're able to kind of find the average if it's like they're all equally weighted, or if one particular function or process matters more in the model, you're able to weight it at a higher percentage, which allows the activation function to be more accurate as well as less confusing when we're trying to call our models and see some actual information at the end. So that's like essentially how the activation function works and how those signals go from an input through those processes to something we can actually use in our machine learning model, and have a better understanding of like overall like what's going on in the model before we just start coding. Also, I wanted to note that nodes and edges have a weight that adjusts as the learning occurs. So they may start at an equal weight for all 4 nodes, but potentially halfway through the process, the model starts to learn that that's maybe not the most accurate or helpful weighting. So if they're finding that's majorly messing up the numbers and it's not super close to the original data set that is being inputted, they'll start to automatically adjust that weight, and the weight will increase as like the signal changes. So if we're receiving a very strong signal, like a lot of signals, if we're receiving a ton of input here into this node and it's a very strong signal is being sent to the output, that will increase the weight, as well as just kind of looking at like how accurate the activation function numbers are compared to what we're receiving. And that will be done more so in the testing like area of our model, but it does kind of happen and adjust like as the model learns more and more. Kind of like I mentioned earlier, the different nodes or neurons are aggregated into different layers. So the first layer is input, and then we have the hidden layer, which can contain multiple nodes if it's a deeper model. But for more like simple models, it will just be the one hidden layer. And when signals are traveling, they'll go from the input to the middle layer, passing through all these intermediate or the hidden layers on their way to the output, which is the final one. Deep neural networks are comprised of neural networks where there are at least 2 hidden layers. So it would be going from hidden layer to hidden layer, adding more complexity into the neural network, where the activation function would need to be properly weighted in order for us to get like good information or good data at the end of it. A little bit about what neural networks can be used for. I know it's kind of like a more complex topic in machine learning, but neural networks can be used for predictive modeling as well as like adaptive control. So if you're thinking of like how self-driving cars are like need to be adapted when they're like controlling things, because there's like a lot of information that they're taking in, like when they're driving on the street, this can be an application of neural networks because there's like so many complex variables they need to take in and process in order to like actually drive. And a really cool thing about neural networks is they can learn from experience and derive like conclusions from the information you're receiving in a very complex and like seemingly unrelated set of information, similar to humans, where if we are finding a pattern in a set of data or a set of experiences that like seems to be unconnected, and it may take a while for a proper explanation to come out of it, but it's very interesting how they're able to take, or the model's able to take such complex information, and through all of the different connections from the input to the different processes, they're able to come up with really interesting and just like unexpected conclusions. And then like when we go back and kind of like dive into it a little bit more, you're able to see like where those conclusions are coming from at like a very like rapid pace, which is cool. All right. Are there any questions? Some people are enjoying the graphics. I love to hear it. 404 got Spotify Premium and listening is up over 100 hours a week. I'm excited to hear that. I don't know what my listening time is over the week, but I'm not quite sure if it's 100 hours. I listen to a lot of podcasts and music on my walks, but it kind of like ebbs and flows as my schedule does. This is a good question for Dimmer. I'm assuming that this kind of flowed in after their stream ended. How do you apply neural networks in games? Do you need to allow it with learning through different games? Do we need to allow it with learning through different games? That's a potential application. We'll be using it in a relatively simplistic way just because it's throughout the course of Global Hack Week as opposed to over the course of several months. We'll be using it to kind of form connections to generate characters' names as well as kind of generate characters' backstories and physical appearances based on a bunch of information we're giving it. But if you're looking to kind of like find commonalities in games, potentially if you're trying to make your own, you can find similarities or like great features in existing games to generate or kind of inform the decisions you make about your own game design. So I think like that would be a really cool one, as well as for actual gameplay. I think that neural networks can be pretty broadly used because it allows for kind of like the computer player or like whoever's playing against you to create like have more complex decision making skills without being a human, because there's so many different aspects of something like the only things I'm thinking of are like games like Call of Duty or Fortnite, where there's like a lot of like different inputs and like situational aspects to it, where neural networks would be very useful because it would be able to process all of that complex information and kind of find like a play to make or how to respond to it. All right. So now that we have a little bit of a base knowledge on neural networks, I'm going to dive into recurrent neural networks, which is what we'll be focusing on today. So essentially, recurrent neural networks are just normal neural networks that are designed for sequential data processing, which sounds really confusing and super complex, but the gist of it is that it's a normal neural network. It falls under deep learning, but recurrence is happening. So as you can see here, the hidden layer is made up of 2 layers. So we have hidden layer 1 and hidden layer 2, but what recurrent neural networks are doing differently than traditional neural networks is they're solving the problem of like no memory of like what happened in the past. So in traditional neural networks, they'll be receiving a signal like at this level from this like initial level, but they won't necessarily remember how it got there, like what the input data was. In recurrent neural networks, they're able to kind of combine the feedback that they're receiving from the initial layer with the input. And it allows for like more complex decision making. And because of the context, it's able to happen at a more rapid pace. Like just because everything is like happening like at a recurrent level, and there's like more context because there is like memory of like what's happening in the past when it's kind of like recurring. Awesome. So a little bit of a basic of like the types of recurrent neural networks we can incorporate. Now that I've kind of given you a little bit of an explanation of basic neural networks and recurrent neural networks. So types of recurrent neural networks would just be traditional ones that are kind of illustrated in this image. There's also long, short-term memory. We might get into this if we have enough time throughout the course of this series. I'm not sure if we will, but we will be getting into gated recurrent unit RNNs, GRU for short, or LSTM for short. Gated recurrent units, I'll be explaining in a little bit. These are all applications of recurrent neural networks as like the specific models. As far as like how you can apply like RNNs into machine learning, it's used pretty frequently in natural language processing because language is so complex. These types of models are super helpful because they're able to compile like the like ever evolving like aspect of linguistics with like how the human brain works, because language is so tied to how the human brain works. So like that's a pretty popular application. We'll be doing a little bit of that with our like overall like character building with like their backstory, potentially tying them together if we have enough time So that's one application. Another application would be time series analysis, which, if you're unfamiliar with time series analysis is a method for interpreting different data sets that is sequentially timestamped. So it provides information that's unrelated to the time, such as maybe a player, like that, like whatever move they made and how many points they scored. I'm thinking of like basketball, for example. So say, like LeBron James scored like a free throw, like earning like a certain number of points, but it's time stamped at this like a particular time, and then other teammates like on that basketball team and the fouls they may have incurred or other moves they made in order to gain points for their team could be sequentially time stamped. And basketball coaches could use that information to gain a little bit more insight into their players, as well as like how the game is flowing. If like everything is time stamped, maybe they're finding out that certain players are performing better during like a certain timestamp. Maybe they separate it up into the different quarters, and they're able to see how like different players are performing, as well as if there's any particular type of, I guess, like play that is like more popular or more beneficial during like a certain timestamp period. And of course, like there's different variables that like would change that, such as the opposing team, the players on that team. But I think like that would be a pretty interesting example. Time series analysis could also be applied, I guess, like pretty commonly to stoplight and like speeding data, because that is like very, I feel like, time dependent for kind of like traffic patterns and the like, because you have like the action of like someone running a red light, someone running a stop sign, any collisions that might be happening, like if vehicles are speeding, how much over the speed limit are they going, and like at what times are these occurring, like what months are these occurring within, but also like the time of day. And of course, like that would be like more heavy during like heavy commuting hours or on the weekends potentially. But it would be interesting to see if there's any other insights you might be able to gain from a time series analysis. So recurrent neural networks can also be applied in player action prediction, which is essentially when a model is predicting whether like what plays an action or what actions a player is going to take through a game, as well as a few other functions in gaming we will get into in a little bit. That's kind of an overview of how you can use recurrent neural networks. And if you're curious to learn a little bit more about the overall math behind recurrent neural networks and how they're applied at like a more deep level, I have a link on the slides that you'll be able to access at the end of this presentation. I'll have a bit.ly link y'all are able to access these slides at after the workshop is over for today. All right, so here are some game-specific applications of RNNs in games. Since it's Games Week, I wanted to emphasize how specifically these can be used in games outside of like what we'll be doing today. So recurrent neural networks can be used to predict player actions, kind of like I talked about earlier. And this is based off of the historical sequences of gameplay. So the model is fed all of the historical information on a particular user or a particular maybe type of user. So for example, like someone who's from a specific country, maybe someone from a specific country is interacting with the game like in a different way than people who are completely across the world, age ranges, as well as like how recently they installed the game. Players who have very recently installed the game are unlikely to be as familiar or as advanced as people who have like spent years playing the game. A super simple example is on Candy Crush. One of my favorite games is when they have like those suggested moves, which I don't often take just because they typically won't be like the most optimal or like the best play, but they will like allow you to like have 3 candies or more be combined. When I originally made these slides, it was a GIF that was moving, but I think that it got compressed when I downloaded the slides. So just know that it had an example of the candy that was moving to like suggest that you should take that play. Another application of recurrent neural networks in gaming is generating dynamic in-game narratives or dialogues throughout the entire game. That's a lot of information for game developers to create, is the entirety of dialogue for a game. It's of course been done before, But for games like where they want it to be more robust or add additional context or maybe personalize it a little bit to you based on like the previous moves you've made or what's going on in the game, recurrent neural networks can use previous gameplays and the in-game narratives or the dialogue that was happening then to kind of show suggestions. I have an example right here. It's a little bit too small for you to actually read what it's saying, but it has a dialogue box over a Stardew Valley game. All right. Another application of recurrent neural networks in gaming would be to detect cheating, which is done through anomaly detection. So, for example, this is done if a ton of new players are joining a game unexpectedly at one time, or if the player is taking a very odd sequence of action compared to how they typically play or how other similar players are interacting with the game. And it's done through one, the anomaly detection of like something's off here, but also doing analysis on the player and like their previous behaviors. So they're able to kind of not only contextualize how they're acting with how game players are typically like behaving in a game, but also looking at like how this specific player has behaved in the past or is currently behaving and like why this particular action or behavior is an anomaly and might be linked to an instance of cheating in the game. So I think that's pretty interesting. Looks like we have a question. The dialogue changed based on an input they selected earlier in the game. Yes, that's the perfect example of like in-game narrative or dialogues. So if they they essentially made an action or did a certain behavior that was selected as an input and put into the neural network. So for example, in Stardew Valley, it's been a while since I've played, so I'm going to use the example of like I guess like the most similar like that I like know well would be like those like Papa's games. If you've ever played like those like Papa's Freezeria or like Papa's like Pizza House or like whatever. Like if you're selecting certain customers or you're interacting with customers in like a particular way, it might change the on-text dialogue. For example, if like someone is, I guess, like killing it with like how they're interacting with customers and like the Papa's Freezeria game, it might provide kind of like a message of like reassurance of like how they're doing and to kind of keep up the good work. But if they're like frequently burning the pizzas in pizzeria, it might change like the dialogue or like the context that it's providing and like what happens in the game. And like in those games, like there is like certain like story like plot points. Those could change based on their behaviors as well, like with this application of neural networks. Awesome question. All right. So now that I've done a little bit of an explanation of neural networks, showed y'all how recurrent neural networks differ from like the traditional ones and showed you a little bit more insight into recurrent neural networks, I'm going to talk to you about gated recurrent units. So this is a slide that needs to be updated. Let me check what I did wrong here. Bear with me. All right, it looks like I did not update the slide to actually show y'all what gated recurrent units are. So we're just going to skip over this for right now, and I'll dive a little bit more into what gated recurrent units are in the next part of this series. But for right now, we're going to move on to actually coding, where we're going to kind of like start the data preparation, and I can explain a little bit more of the concepts in the next stream because we did a little bit of a basic explanation of what RNNs are. I think like now is a pretty good time to move into the data preparation of this. So I'm going to move over to GitHub code spaces. Don't fear about like where it says GitHub link right here. I'll be updating it in just a few. But if you do want to kind of follow along with what I'm doing, you are able to access the code at the end. And if you just want to type everything up, kind of like as I'm talking y'all through it, you can just open up a Jupyter notebook file, whether that be in Colab or locally in Jupyter Notebooks. All right, it's loading, starting up that code space. While that's installing, I'm going to give y'all a brief intermission to get your Jupyter Notebooks set up, grab some water, or head to the bathroom really quick. We'll be back in about 2 minutes for after our intermission to get started with our data preparation. I'll see y'all in just a few. All right, I'm back, y'all. I hope you're able to have a chance to grab some water, get your Jupyter file set up if you're trying to follow along with me. But if you just like kind of want to watch, that's all right as well. I'll be sharing a link to this code on a GitHub at the end of the stream today. All right, so let me open up my Jupyter notebook file. As you can see here, it's just kind of an empty code cell. I'm going to get started by adding some import statements. So import statements. Oh, I always hit shift instead of enter on this. And also, for if anyone's curious, I am typing all this up in GitHub Code Spaces, which is a browser version of VS Code. I really like it. It makes streaming with y'all a lot easier. I'm able to, as well, just kind of like access everything in a pretty like standard development environment without very many like compilation or version differences. For the person that asked to zoom in, does this look better for you? Let me know in the chat. I think I'd put it to like 110%, but I can make it a little bit bigger if you need. All right. Looks like some of y'all enjoyed some chai over the break. That's great. Okay. I'm gonna make it slightly bigger just to make sure it's good, but first thing we're going to do for our import statements is we're going to import a few different libraries that will be very helpful throughout our development process. They're pretty common libraries that are used in machine learning. First is going to be import NumPy as NP. Second thing we're going to do is import pandas as PD. And after that, we'll be importing TensorFlow as TF. I'm going to turn off these auto recommendations just so I don't accidentally shift my way into the wrong import statement. So, okay, I'm going to turn that off, and it should be working all right. Perfect. Okay, so now we're going to import a few different TensorFlow libraries because you need to import them kind of like at like a deeper level for what we'll be using. So the first thing we're going to do is import the pad sequences as well as a few GRU layers. I'm going to go through the entirety of this name generation today, and we can explain a little bit more about GRUs tomorrow. So from TensorFlow.keras, and then we're going to go even deeper into layers, import GRU. We're going to be importing dense and also embedding. Beautiful. And then again from TensorFlow. I'm just realizing I spelled TensorFlow wrong up here. So I want to catch that before I have any silly errors later. And then also from Keras, we're going to go into the pre-processing sequence. And we're going to import pad sequences. All right, I'm going to run this. And I'm going to install the Jupyter Notebook extension that they have on VS Code. It's just not installed because I don't already have everything synced to GitHub Codespaces. For my Python environment, I'm going to choose just 3.10. Most of the older machine learning libraries tend to work pretty well with 3.10. Sometimes if you get into newer things, they're not always supported. Looks like there's an error. No module named TensorFlow, which means we need to install TensorFlow into GitHub Codespaces. If you don't have TensorFlow already on your computer, this is also a good kind of like rule of thumb to follow. You're going to be typing in pip install TensorFlow. If you don't already have pip installed on your computer, I'd highly recommend it. It's a package manager for installing all these different libraries. I use it when I'm doing things with machine learning and Python, but I also use it pretty frequently when I'm doing things with JavaScript and different things with Node. I found it to be a lot easier for managing all of that. All right, spitting out a bunch of green, which is great to see. So downloading a bunch of sub functions from the library. That's great to see. All right, it's buffering. In the meantime, I'll make sure I haven't missed any questions. All right. Okay, it looks like the installation is done. Let's run this code one more time. It's thinking. Another error. This one I think is probably just a spelling error. So let me bring this over and just place it. I don't think there was any. Okay, yes, that was just a spelling error. So wrote in the correct spelling pretty quickly. And we're all good. There's one more import statement that I need to do. So from tensorflow.keras.util import. And for this one, we're going to be importing two categorical. So for both the preprocessing and the util, these are both functions that we'll be using throughout our model to kind of like make things run a little bit smoother. For here up in TensorFlow .layers, these are just different layers that we'll be having in our RNN. And then I'll run this one more time, make sure no errors. TensorFlow keras.util. Oh, I'm missing an S. Beautiful. Okay. And for the person who asked, what was the pip statement? It's pip install TensorFlow. I will put that in the chat as well. All right. So now that we have the import statements, we can actually start pre-processing our data. So I'm going to make a new code block to make everything pass a little bit easier. It's a little bit easier to follow. For me, things are separated. So first thing I'm going to do is actually make a sample data set of character names. If you're comfortable, feel free to throw your name in the chat, and I might enter a few of y'all's names into our data set. For right now, it's just going to be a basic Python list, but I'd like for it to be as long as possible. So feel free to share your name in the chat, and I can add it into our character names. So first thing I'm going to have is just a simple list of character names. My name is Gabriella. I know that we have a lot of Ryans. I'm just listing off different MLH coaches right now. But if you'd like to add your name, feel free to put that in the chat as well. All right, we have Alan in the chat as well. And now I'm just going to type up a bunch of names. Sarah, Eliza, Aaron, Katniss. I did not close that quote. Henry, Ava. Let's do Alice, Bob, John, Alberto, let's see if anyone else has shared their name in chat. We have Marcos, Vex, Zach. Let me scroll up a little bit. 404. I will put not found. We need everything to have like alphabetical characters for our name, so I can't put numbers in, unfortunately. Shabazz. I wonder if it's gonna mess with it with the spacing. We'll see. I'll just put Pharaoh with letters. All right. Looks like we have all the names in there. I'm gonna add in a few more just from my, like whenever I was testing this out to begin with, kind of prepare for this workshop, just so we have some more names in here. Mia, Catherine, Pharaoh. Oh, no. Okay. Here we go. Ivy, Jack, Emily. I don't think we have Henry. Do we have Henry? We do. Okay. Bob, Charlie, let's see. I'm gonna quickly type some more in just so we have more information for it to train on. I don't think I did. Okay, just one. And then I will maybe try doing 404 instead of not found. I think the spacing is going to mess it up. Do 404. All right, I think this is good for our initial list of names. We can add in more or potentially even find like a baby names data file for later on. I just want to have kind of like a more simple data set to begin with, and I can show you how the neural network will actually work before we dive into more complex data processing. 404 is happy to be included. Love to hear that. Run this. Looks like everything's going good. So now that we have our character names, we need to kind of like create a vocabulary from them. So it's able to understand all the character names kind of like represented in a little bit more of a simple way. And it's kind of creating this vocabulary based off of these names. So the names will be slightly similar to the structure and the characters that are made up in this particular one. So we're going to create a vocabulary based on the sample names. In order to do that, what we'll need to do is create a vocab variable, and we're going to set that equal to the character names being sorted and put into a specific data type. So we're going to use the sorted function, and then we're going to put it into a set so it's easier to process for our model later. And then to kind of process our names, we're just going to have our like empty string where we're joining the entirety of our character names. This is going to put all of our character names into a set, so it's easier to go through and process and create a vocabulary based off of this. And then after that, we're going to need to actually index each of these characters and kind of like pair those together. So I'm going to make two variables, one where I'm mapping the character to the index and one where I'm mapping the index to the character. This will just allow for easier access later on. So I'm going to have char to index as well. Oh no, I hit shift again. I need to stop hitting shift when I need to hit enter. And then we'll have index to char. These are both going to be in object-like structures. And inside of that, I'm going to have the char, the index, and I'm going to run a for loop to find each index for the particular character. So here we're going to have char, and then we're going to set that equal to index for index in our particular vocabulary. But that'll be done by enumerating it, so we're actually able to find the different indexes in vocab. All right, looks like it's taking that. Everything seems to be looking good. We're going to do the same thing down here, but with index, and we're going to do char for char in our vocabulary. And we're going to do that by just finding the items of each of these. So we're going to go char to index dot items. And we're going to find all the different items in here that we'll need. And I also want to add in the index as well, just to make everything more accessible. All right, so it looks like everything here is going okay. I'm going to run this code again. Oh no, we have an error. Char is not defined. Interesting. Interesting, interesting. Have not seen this before. Because it's being defined inside of the object. All right. Have our character names, our char. Oh, I think I see what's going on. I did not follow the same logic for both of them. So they both need to have the index in the for loop as well as the character. There we go. It's happy again. It's always the little stuff. Are there any questions so far? Oh, someone's having an import error. Cannot import name to categorical from TensorFlows. Are you getting this on your end? I think I was having an issue similar to this, and it was a spelling error. Okay, it's fine now. Perfect. Okay, awesome. So we can just keep tracking along. After we've made that vocabulary from those character names, we want to convert the different character names into sequences of those character indices. So we're able to kind of like ensure that everything is like an equal length later. And if we have sequences of these letters, it's easier to find an equal length and have everything like look like a normal name essentially. So we're going to declare these different sequences from our character names. So convert character names to sequences. I keep hitting shift, that's okay. And we're going to set sequences, just sequences. And that is going to be equal to a list where we're going to go through a for loop where we're converting those character names to the specific sequences we'll need. So we're going to have a nested list right here. And inside of that nested list, the first thing we're going to have is we're going to be calling char to index at a specific index. The index we're going to be calling it at is a specific character. And then after that, what we're going to be doing is looping through and doing that for each individual character in the name. All right. And then on the outside of our nested for loop, we're going to run through this for loop and we're going to go through each name inside of our character names. So this is initially running through each name and character names, and it's going to index those characters, converting them into sequences for each individual character in the name. So let's run that. Looks like everything is going pretty well. And the next thing we're going to move on to is actually padding those sequences to ensure that we have an equal length of the sequences and kind of an equal length of the names like after they start to be generated. So we're going to create max name length, and this is just going to be equal to the maximum length of a name. So that's pretty easy. We just have to do max length, and then we will go through our sequence and do for sequence in our sequences. Beautiful. Okay, so this particular section, like I said, we are padding our sequences to ensure equal name length later. All right, let's run this. Looks like everything's going well. Looks like we have a question. How did I fix the char not found error? I got disconnected. It's a great question. So the reason I was getting the char not found error was on this line right here, char to index, this particular variable. I was looping through each index, I was returning the index for each of just the index in enumerate vocab. But when you call the enumerate function or any function, it's a good idea to have both the index and the character. So I did not have the character right here. So after index, if you were following along with me, you'll likely just have everything here besides comma char. So just add in comma char and you should get rid of that error. All right, hopefully that was helpful. And now we're going to continue padding our sequences so we can ensure that equal name length later. So now that we have our max sequence length, we need to actually pad the sequences. So we'll have padded sequences, if I can spell. That's definitely not how you spell sequences. Just going to copy this, I'm going to be honest. There's no spell check in the VS Code. All right, so now that we have padded sequences, I'm going to set that equal to us calling the pad sequences function. As you remember up here, we imported pad sequences from pre-processing. So this is just going to run a function where they will pad the sequences on the TensorFlow end. And we need to call in a few things so it knows what to do. The first thing is our initial sequences variable. The next thing we need to let it know is essentially what our max length is and how, where we want to put our padding. So our max length is going to be equal to max name length. And for our padding, we want to add it to just the end. So I'm going to put just post. So it adds that padding towards the end and we can just kind of trim it off as need be. It says it'll probably pad all names to 9 characters. I'm curious. Let's see what the max name length is. So I'm gonna have it print max name length. We can comment this out later. I'm just curious how. Oh, 10 characters. So you were pretty close. All right, I'm gonna just comment this out for the time being. Now that we've padded these sequences, we can actually start to create the input and the target sequences for our model and actually start building out that model. So first thing we're going to do is click X and Y. So those are the 2 different inputs we'll need for our particular model. And I'm going to make a comment, just this is a little bit easier to read. We're going to create input for our sequences as well as a target. This needs to be lowercase because that's how it typically goes. Just in machine learning, padded sequences as well as padded sequences. And we're going to do something pretty similar for the X and Y variables. We're just going to be accessing padded sequences from the beginning. We're going to be slicing it. We're going to be accessing it from the beginning, but we're going to want to reverse everything, which is what that particular index is doing. And then for the other one, we're just going to want to slice it a little bit differently. So we're going to have semicolon as well as everything after the first index. Let's run this. Everything seems to be running well. All right. So now that we've done that, we need to make sure that we're all the things with the padded sequence, our target, we're all kind of in line. If you've ever worked with machine learning before, you'll know that your input, your output, as well as the different variables need to have similar bounds so it's actually able to process all the data. And you can do this pretty easily by just saying print x.shape. I'll also print the y shape as well, just because I'm curious, but just to ensure everything is going well. It looks like they have the same sequence, which is great, which means we shouldn't run into any issues later when we're actually running our model and training everything. All right, and just to make sure that we have everything properly documented, type check the shape of our input sequence, and then check the shape of our target sequence. Beautiful. All right. So now that we've done that, we need to actually encode everything, and we're going to encode our target sequence into a one-hot encoding. Into a one-hot encoding. We're going to do this just by declaring a new variable, and then we're going to use one of those functions we imported earlier from TensorFlow, which is toCategorical. And inside that, we just need to provide a few different characteristics so it knows what it's doing. Our target characteristic, as well as the number of classes we'll have. It's going to be equal to the length of our vocabulary. All right, let's run the code again. No errors, seems to be doing well. All right, we're just trucking along, aren't we? Okay, so now that we've done this, we need to actually start defining some characteristics of our model. So I'm going to set the size of our vocabulary equal to the length of our overall character names, which makes sense. It's just kind of like this is just a characteristic that the model will need. So we're going to set the vocab length equal to the length of our vocab. And I'm going to change this to size because that's the exact verbiage that the model will want. So that's essentially what we'll need for that. And then don't worry about this right now. This variable called embedding dim. This will just essentially make sure that the character generation model is working how it should be. So we are defining characteristics for our GRU-based character generation model. All right, let's run the code one more time. No errors. We're doing just excellent. So now it's time to actually create the model. The exciting part, but it doesn't actually take that much time or code. So we're just going to set the model equal to a parentheses inside of a parentheses that has this bracket inside of it. And then we're going to be calling some of the TensorFlow functions that we imported earlier. So we'll call our model just like this, tf.keras, and then I'm going to be calling sequential. So this sequential model is pre-built into TensorFlow, and we just need to import the different information that we just defined by sequencing out our different characters. All right, looks like I'm out of water. Time to move on to my sparkling water. I have the raspberry one from Trader Joe's. I quite like them. All right, so inside of this sequential model, we need to declare a few different things. So, I hit shift again. All right, enter, enter. So up here where it says keras.layers, you see GRU, dense, and embedding. These are all the different functions that we'll be using within the layers to define things and build out our model. So the first thing we're going to need to declare is the embedding. So I'm going to type out embedding, and we'll have this parentheses. We're going to add some additional information into this function. So the input dim, if I can, input dim is going to be set to the size of the vocabulary. So this is just kind of showing how big the input is going to be, so it knows how big of a neural network to create. And next, we're going to say output dim, and then we're just going to essentially say how big we want our embedding dim to be. This is how big we want the output of our neural network to be. That's what that 32 comes from. It's a little bit arbitrary, but we want to make sure that it's like not outputting too much information when we're just kind of getting started. And then for the input length, we're going to have that be equal to the maximum max name length. And then after that, we're going to move on to the GRU as well as the dense characteristics. GRU and dense. So inside of GRU, this is our gated recurrent units. We're just going to input a few pieces of information really quick. 128 as well as return sequences will be equal to true. And then the dense function, all we need to input is the size of our vocabulary. And then after that, we'll need to add in or input an activation variable that will be equal to softmax. All right, and I'm going to run this. Looks like we're getting an error. Unrecognized arguments passed to embedding, input length 10. Maybe Marcos was right. Maybe it does need to be 9. Let's see if that fixes it. No. Run. Okay, where's the error coming from? Embedding. Input length 9. Let's see. All right, so we have our max name length. Make sure I'm declaring that correctly. No, that should be correct. Vocabulary size is correct. Embedding dim should be 32. All right. Am I doing everything else correctly? Embedding grew and dense vocabulary size equal to softmax. I want to run it one more time. You just make sure nothing else is going wrong. All right. All right. I'm not quite sure what this error is. So before I go hunting on Stack Overflow, I'm going to see if Copilot has any answers. Let's say explain. I'm going to put this error in. All right. The error message you're seeing indicates that the embedding layer in Keras doesn't recognize the input length argument you're passing into it. So it does not recognize max length or max length -1. The input length argument is used to specify the length of input sequences. It's optional. However, the error message suggests that the embedding layer doesn't recognize the argument, which is strange because input length is a valid argument for this layer, according to Keras. This could be due to a few reasons. It could be using an older version of TensorFlow or Keras. There could be a typo. Input length is spelled correctly. Let's make sure that max name length is spelled correctly. Yes, it's the same variable about. We printed it out earlier. Maybe I need to print out the type and see what the type is. Maybe it's not an integer, and that could be the issue. No, it's an integer, so that, okay, that's not the issue. Okay. these are all being passed correctly. Embedding. All right. Okay, since this is optional, I'm going to take this out really quick and see what happens. Okay, it runs. So I'm going to see how it runs without having the output length or the input length there. Maybe we weren't able to pad everything else. Yes. Pharaoh asked, where is pad sequence defined in the script? I believe it's up above. Pad sequences. Okay. Pad sequence is the function that we are importing from TensorFlow. So that's not something we need to actually define it in the script. We just imported it up here, and then padded sequences was the variable where we were actually calling this function onto our actual sequences. Yeah. All right. So I'm going to make a note of, so we created the model, running into issues with input length in our embedding function inside the model, and return statement said it did not recognize the variable / wasn't a valid integer, but when printing the value type, it returned int. All right, so this is for some context for later, potentially for some troubleshooting tomorrow. But we're going to keep trekking along and see how this model actually turns out to be, even though maybe it's just like the padding that kind of like ran into an error. Okay, so now we have this model built. We want to actually compile and train it. This is just like this block of code is the actual model, and it's declaring everything, but we're not actually like deploying it to anything. It's not being run, and it's not in action quite yet. It's just like declaring everything we need for this model. So after that, we need to train the model, and we'll also need to compile it so it's able to be trained. So compiling goes before training, and both compiling and training the model are pretty simple. So for compiling the model, we'll just call a function onto the model variable, and it's just going to be compile. So you can see here is one of the suggestions. We do need to add a few extra things into this. So we're going to optimize it with Atom, and we're going to specify the loss to be categorical cross entropy. Not like that. Categorical cross entropy. Run this. Okay, looks like the model is compiling all right. Next thing we need to do is actually train this. This is when we're going to return a lot of epoch statements after we actually train the model. So what I'm going to do is I'm going to call the model again. This time, instead of just having it say train, I'm going to say I want to fit the model, and I'm going to be fitting the model to our actual data. So this is going to be our x variable, which is the input, our y, which is our specified output. And then we're also going to have our epochs and verbose set to different variables. Epochs will be set to 50, and we want to set our verbose equal to 1. And this we need to have set to 1 hot, so it's all the same length. All right, let's run this. And you can see the epochs are starting to return. Looks like we're going good so far. Okay, all the epochs are running. So that's awesome. We just declared everything for our model, and we compiled the model, and then we trained it. So now we have a trained model. The next step we need to do is actually deploy the model. So in order to do this, I'm going to make a new variable, and we need to define something called a seed. And this is essentially where it's going to be starting on this. In this particular language model, we can show a seed to be the start of a particular character. So for this particular one, I'm just going to do A and see what it spits out. We can test out and see what it does if the seed is just an empty string, or if we do more than one character, how that kind of like outputs it. This is just like where it's starting the name generation. So it'll start generating A names. The next thing we need to do is create a seed index. This is just making an index of all the characters after the seed letter. So seed index will be equal to a list. And similarly to last time, we're going to use char to index. We're going to access the index char, and we're going to have a for loop for every single item inside of the seed. So for char in seed, we're going to go through and index all of these. It's going to be a pretty simple list because there's only one seed character. But if we had a longer seed character, or if potentially we had multiple seed characters, we have someone who has multiple names, someone who has, we're trying to generate like a first, middle, and last name, someone who has like a hyphenated name with like multiple last names, multiple middle names. Some like religious people also have confirmation names or other religious ceremony names that could be used with the seed to generate those based on different like starting letters. However, right now we're just going to generate first names to keep it nice and simple and make sure that we're avoiding any potential errors in our first part here. So now we have declared our seed as well as the seed index. Scrolled up, okay. Enter, declare seed character, and then we want to map our seed characters to indexes. And then after that, I'm going to have a for loop. So this is going to be looping through each, like from 0 to a particular range. So it'll have, like we do like in range 3, it'll have 4 characters. We do 4 blank in range 3. This will just have some simple 4 character names. We can make it longer as we go through and kind of like adjust this a little bit more, but I'm just going to focus on kind of like the basics so we can get some names generated in a little bit. So next thing we need to do is define the temperature. And the temperature is essentially a variable that controls how random the generated text is. So a 0.5 is like relatively random, and the higher you and closer to 1 you get, the more random this is going to be, just because the temperature is set up higher. If we want something that's like a lot less random, we could do something like 2.5 or 0.25. But for right now, I think 5 is like a pretty good middle ground. And then I'm going to bring in some different information for the predicted parts of this. And I'm just going to have these be called predicted names. And I'm going to set that equal to us actually predicting something with the model. So we're going to call a model, and we're going to use the predict function. And inside of that, we're going to actually need to input some things. So what we're going to input are a different set of information from our seed. So I'm going to use the NumPy array function just to kind of manage that data flow. And then we're going to put in the seed index. And then after that, what we'll need to do after we have that seed index is we're going to need to reshape it so it's a little bit, it's like more focused like a string would be. So we'll reshape it. We're going to have 1 to -1 at index 0. All right, so that's being reshapen. I think I misplaced a parentheses. Yeah, okay. We should be good to go for that. And then this I should have changed though, because we're working with probabilities still. These are probabilities that like the next character should be in the next part. So after that, we're going to take the last set of probabilities and we're going to use that to make the next prediction. So we're going to overwrite our predicted probabilities. and just set that equal to the last item in our list. All right. I'm going to add in some comments just to explain everything. So here, actually calling our model, finding the probabilities from the model, generating a name, higher the temp, the more random output will be. And then here, for predicting our probabilities, we're going to be taking the last set after we find them. From model. And then after that, we're going to go through a few different math functions in order to make sure that our predicted probabilities is just like in the right format for what we need to do in order to like actually print it out. So predicted probabilities, we're going to overwrite this one more, and we're going to use NumPy. We're going to use the power function. And then set it out, we're going to input predicted probabilities, and then we're going to have 1, and we're going to divide 1 by the temperature. So this is kind of fine-tuning our probability to the power of our temperature. Then after that, we're going to overwrite predicted probabilities just one more time. We'll have predicted probabilities, and we're going to make that equal to the existing predicted probabilities divided by NumPy, and we're calling the sum function. We're calling the sum function on just the existing probabilities. All right, so let me run this. Doesn't seem like we're getting any errors, and it looks like the function is being called properly as well. So we've gone through all those predicted probability steps. We're super close to actually getting a real name. So next thing I'm going to do after that is we're going to add the next character that we're generating to the seed to actually make a name. So we're going to do seed plus equal to the char. And this will actually show us the next character that we're generating. I just realized I did not actually declare next char. So that would be a problem. So we will declare next char by randomly choosing one of the different letters that we have in our model. So we'll do NP, do sum, and then we're going to, or not sum, I'm getting confused. Random, we're going to randomly choose one of the letters. And that's going to be from our list, of our characters mapped to the index. So we're going to specifically be accessing the keys, which are the different characters. So char to index dot keys. Okay, and then this is looking good. And we want to make sure that the probability that we're selecting each of these is equal to the probabilities we overrided and kind of fine-tuned specifically so it would be in the right format. So we have our predicted probabilities coming from our model up here. And then down here, we're taking this randomly generated character that we get right here from the random choice model. And we're adding it to our seed. So all of these names are going to start with the seed A. If we decide we don't want to have a guaranteed first letter, we can get rid of that. All right, so now after we have all this, we're going to need to actually append everything into our seed index to make sure we have this running for the entirety of the loop. So after that, we're going to go to seed index at the specific index of our next character. But we're first going to be appending this, and what we're going to be appending is the specific index of our next character. So next character that we're adding to our seed, this is what will end up getting printed out. We're also mapping into our index. We're able to properly move through everything in this range. So as it gets updated, the index is automatically updated as well the next time before it runs through the loop again. All right, so now it's time to close out that loop and actually print out our generated name. So I'm going to print the seed. And then let's run this. All right, so it looks like the generated name is Ahar. Let's see what it comes up with next. I'm going to minimize this Copilot tab really quickly. I'm going to run this one more time. We just have a bunch of A letters, so we see it's not perfect. And then run it again, getting a bunch of A's again, bunch of A's again. We're getting aha, A. Let's see what happens if we change the seed to be empty. Okay, I'm going to just have it be a blank string. Another blank string, key error. Okay, it's because there's no actual character. Let's do AX for our character, for our seed. Okay. AXAA. AXAA again. I'll make this a little bit shorter and have it be in a range of 2. So we have some 3-letter names, and I'm going to change these to start with a C. See what it comes up with. CXL, CSA, Che. Okay, so we have getting a few actual names here. CNY, CBA, CA. Let's go back to range of 3. All right, CXAA, Quan. It's like cicada, but like not cicada. Psycha. Sonoa. Ka again. Awesome. So you're seeing that like it's kind of like going back and forth between like real names and like just like a bunch of letters. This is due to our model being fairly simplistic, and also we don't have very many names or like a great diversity of names. I just kind of like took these from like a basic list of names, and in combination with what y'all shared in the chat, as well as like it's like literally 2 lines or 3 lines, and there's lots of names. So I'm gonna add in a few more names. So do Bert, Juan, Jose, Chris, it's probably not going to change that much because it was like 3 names, 4 names, but we're retraining the model. Let's see this. All right. Cool. I'm going to alter the temperature and see how like changing it to be higher or lower will affect it. So I'm going to make it lower. So that means that it's going to be less of a random output. All right. So we have CAA again, CRIA, CNA, CTRI, CIA. Okay. Cool. I'm going to put it higher. Let's go to 75 and see how much more random I think. I think that part of the reason that we're getting so many repeat letters is partially due to it being like a pretty short like name, as well as the variety of the names we have in our list and the temperature. Let's see if we like increase the temperature, it might get to be more random, so the different letters are more unique. So we have clue, not a name, but a word. CJTA, CYYR, CPTL, CDUA, CPOP or CPOB, CIIB, 0. Okay, so let's make it to 5 and see how that changes the names. Okay. Interesting. Let's change it so it has 2. So I'm going to have CH, so the prefix to like a lot of names. Let's see what it comes up with. All right. Chavia. Okay, let's shorten this slightly, back down to 3. Okay, Cheka, Cha. Okay. Okay, we're starting to get a little bit better, I think, as we have been adjusting like little pieces. Looks like Marco said to raise the temperature for more creativity. I ended up doing that. Let's raise it a little bit higher and see how it goes. Let's put it up to 95, which is fairly close to 1, and see how much it changes. Okay. Chirp. Okay. I am seeing a little bit of a difference, though. I feel like it's less repeat characters than we were seeing earlier. Now that we've raised the temperature for a little bit more creativity. I think that's interesting because earlier I was having, like when I was preparing this, I was having the issue of it just repeating like a bunch of lines of gibberish for very long names. So when I kind of like decrease the temperature and the length of the name, it was kind of spitting out like things that were like closer to actual names. But for this, now that we've kind of like adjusted the predicted probability a little bit as well as the temperature, it seems to be making things that are a little bit more closely resemblant to names. Let's run it again. I'm going to start with W now and see how it changes. All right. Interesting. All right. Let's see if there's any questions in the chat. 404 went to bed. Hope y'all slept well. Way is curious what sleep is. I guess Way is a little sleep deprived. Awesome. All right. And then someone wants to see the code for model compiling and training. No problem. All right. So up here, this is the model that we built and all of like the characteristics to build out like the specific aspects of the model. And here we are compiling the model. We're using the atom optimizer and also declaring the loss as the categorical cross entropy. And then we're going to train the model to fit with our input, what we're expecting as the output that is used to the one hot encoding target sequence. So it makes it a little bit easier for the TensorFlow library to read it. And we're setting 50 epochs and making the verbose equal to 1. So we're able to train it on 50 epochs. All right. I hope that was enough time for you to get the model, compile, and fit statements. But if not, don't worry. I'll be sharing the code to GitHub after the stream. Farah wants to see the import statements. Yes, I will go up, leave that for a little while because there are quite a few. We have NumPy, we have Pandas, we have TensorFlow, as well as a bunch of TensorFlow libraries. The ones here in the fourth line, these are the layers that we're using in our neural network. We have gated recurrent units, dense, and embedding for our different layers. Like I mentioned earlier, we'll dive into a little bit more about gated recurrent units tomorrow. And we start generating a little bit more about our character, including their age, as well as a little bit about their physical appearance. So things like their hair color. Do they have really straight hair? Do they have super curly hair? Do they have something in between? And more information about them. So we're able to eventually generate pictures of the character. The Git repository will be on the slides after the fact. I'm going to update it. And I'll be sharing a bit.ly link at the end of this stream. Awesome. Pharaoh got the import statements. So that's good. All right. So I think, what are we at? We're a little bit before 40. We might have time to take in like a Kaggle set of baby names and change that to be the like the data that we're inputting. So let me see if I can find a Kaggle baby name set real quick. But I'm not sure if we'll be able to fully import that and like alter the model. Pharaoh's curious on my thoughts between TensorFlow and PyTorch. I don't have like that many opinions about TensorFlow and PyTorch like comparatively. I've used TensorFlow a lot more. We used it a lot more in my machine learning class last semester. So I don't have like that strong of an opinion just because I haven't used PyTorch all that much in my experience. So I will try it out though and get back to you. All right. It looks like I found on Kaggle a database of baby names. So I'm going to change the screen I'm sharing to be sharing the Kaggle set. All right. So this is the baby name set. I think it'll be interesting. This is a way we could potentially add weighting into our model to make it more complex. I don't know if we'll have time for all the weighting aspects today. I think we'll just have time to maybe add it in and start maybe some simplistic cleaning. But as you can see here, we have the database set, US baby names, and it finds different naming trends from babies born in the US. This was literally just the first thing that popped up when I Googled Kaggle baby name dataset. So here we have an ID for all, looks like 1.83 million baby names. That's quite a lot of babies, quite a lot of names. And there are 93,000 and some change unique values. So I think that's a pretty good data set to train our model on. The year, as well as the frequency of how many babies were named that. So we have very popular ones like Mary, Anna, Emma, Elizabeth. I'm curious if we change how this is sorted, we'll be able to see some less popular baby names. All right. No, sort ascending. All right, so here we have some ones that are at a count of 5. They come from the 1880s, so the names will be quite different, or at least I think they'd be quite different. I know an Adrian personally. Adele, I guess like an uncommon name, but I feel like most people know about Adele with one less L, the singer. Adina, I've met Adina. Albertine, I've not heard that name before. Alyssa, Anna, Ara, Minta, Arthur, Bertha, Bula, Kati. Okay, cool. So we have a good amount of baby names. I am saying that most of these are, if not all, girls' names. Oh, never mind. They just are a little bit further down. Here we have Joe. Yeah, okay. I think this is a pretty good data set for our purposes. I'm going to download it and then I'll import it into our code space. I'm going to switch back over to this slide while I download it. So you will need a Kaggle account to download it, or you can just wait for me to upload it onto our GitHub file. All right. Dismiss, download, downloading the files. All right, looks like the zip file is already done. So I'm going to open up that zip file. Then we can pull out the actual data set. If you haven't used Kaggle before, they add a lot of information into their data sets, which is particularly useful. All that information, kind of providing more context on the different data set variables, is included on README and a PDF that's included in the download. So I'm going to import the information into our repository. I think I need to do that locally though. So give me 1 second. New window. No. All right. Documents. Okay. Okay. Perfect. Okay, so I'm going to copy in that nationalnames.csv into our repository. And then I'm going to commit that to our repository. All right. Data, upload, commit. All right, so that's outgoing and should be pushed. Beautiful. All right, so I think I should be able to show it to you in my file. So once I'm going to push workshop code, commit. Then I'm also going to push and pull to get that data down. No, okay. So I'm running into some Git conflicts right now. I'm going to work through those. In the meantime, I will just show you the rest of the resources. And tomorrow at, I think it's 1 p.m. Eastern, check the Global Hack Week schedule at the website. You'll be able to check out part 2. We'll continue building out what we're generating, as well as working with baby names from across the US. Yes, merge conflicts, the best. I'll work through them offline. If you want to check out when the next one will be, I believe it's 1 p.m. Eastern tomorrow, and part 3 will also be happening tomorrow. Head here, but if you'd like to access the slides from this workshop, you can head to this bit.ly link. I'll send it in the chat as well. You'll be able to access these slides, and if you refresh in probably like 10 to 15 minutes after the stream ends, I'll be uploading the link to that GitHub. But thank you all for tuning in. I had a blast working through recurrent neural networks and our name generation model today, and I'm so excited to work on more character building tomorrow. Thank you all for tuning in. See you tomorrow. Bye-bye.